All right, let's start our class today. Okay, yeah, welcome back, everyone. So this week we are going to continue to talk about Stack Overflow vulnerabilities. And as you already watched for the video, we started with talking about the format of the binary. And the reason why we talk about this is because, first of all, we have tackled many binaries during this class. Every time that we exploit a program, it is compiled as a binary. So it's good for us to understand when we talk about binary, what does it really mean, right? So one is to understand the structure. And also in the meanwhile, from that understanding, we can know how the binary structure was looking at when it is loaded into the process, when it's to be executed by the computer. So that's why we also talk about, okay, how those so-called segments are loaded to the process to become part of the memory. And this will help you to understand things like, when we talk about NX, what does it really mean, right? So it's like the stack itself is part of the memory, which is different from like the codes, which is different from the other places that stores the instructions, right? So that's why computer can set the stack as non-executable, but it cannot set the other places that stores the instruction non-executable because they're loaded separately into different segments. And by the time that the computer sets something non-executable or executable, readable or writable, they're assigning this entire segment as either readable, writable, or executable. So that is the high level of how a binary is look like, how a compiler managed to, compile a source code to a binary. And also, when the binary is loaded to the computer, how does it look like? Why can we set some special interesting defense mechanisms that can, protect this process or protect the program when it's executed, not being exploited or not being, suffered by vulnerabilities such as buffer overflow. Okay, and then based on that, we talk about how to leak libc, right? So if you remember in the last week, we have this ROP chain, right? But then by that time, when we talk about ROP chain, the libc's base address is given, right? You just read it from the string that's sent to you. When I say you means that the client, right? So you receive that base address, you take it as a known value, and then you use that value to add the offsets that you identify through like ROP generation tools such as Ropium or ROP gadget, right? So you find the offset by your own ROP gadget tool, and then you add that offset with the base that is given to you through the interaction of the server, right? And then you come up with the actual address of the gadget by the time that you execute, by the time that the server is executing and interacting with you, right? And then that's why you can use those gadgets and jump to that address and go to the right instruction and execute it, right? But of course, in the real world, there's none of the program that will really give you the value. Hey, this is my base address of libc. And then you have to figure out that base address by yourself by taking advantage of vulnerabilities such as buffer overflow, right? So that's why in our video, I forgot it's the third or the fourth video, but like in one of those videos, the third, fourth, okay, cool. Yeah, so in that fourth video, we show you how you can leak libc's address using a buffer flow vulnerability, right? And then the highlight idea is because by the time that you can by the time that you can overflow and overwrite the return address, basically you can control the program to execute things that you want. So in order to use that arbitrary control power, you can use that arbitrary control to call a function that will output the libc's address, right? And on the high level, this is to call function put with the argument of, a arbitrary libc's function. But then because by the time that the libc was loaded into the process, even though that the ASLR is on, the offset will not be changed, right? It's only the base that will be changed every time, right? So that's why you can find that location with the constant offset, so that by the time that you use your arbitrary control, arbitrary execution power to output that address, you minus that with the offset so that you will be able to get the base address. Does it make sense for everyone? Yeah? Okay, cool. So before we go to today's lab, which you will do Lipsys leaking, you will also do the connection between Lipsys leaking and also the actual ROP. Before that, I want to make sure that you understand what we talk about, especially for the ROP part, the Lipsys leaking part. So if that makes sense to you, then we are going to go to the leaking. But then if that doesn't make sense to you now, I think this is a perfect time for you to start to ask. So do you have any more questions, especially the Lipsys part? No, we're good. Okay, then let's start our lab today. The lab of today, same address, different ports. This time is 6666, and similar as the last time, you have these 4 files all together. The source code is for your reference, and then the other 3 is the actual libraries and programs to be executed and currently being executed in the server. And your goal is that you want to find the vulnerability there, exploit it. And if you run the program, you will notice that the program doesn't give you the base of libc. So you need to figure out the way to leak the base of libc, and then think about how you can chain that base, the leaked base address, with the execv bin slash those ROP gadget together, so that you can finish an end-to-end attack. So for today's schedule, I would say right now it's 10:40. Let's work on this. So I will have you guys to work on this maybe for 20 minutes. Try to leak the libc by yourself, okay? And then starting from 11 a.m., we're gonna work on this together to leak the libc. And if you don't know how to leak libc, still not very clear about it, you can spend this 20 minutes to make sure that your laptop can run this program properly, okay? Because that will help you, and that will be essential for you in the future when you do the assignment as well as today's lab. So you will need to debug by yourself. So make sure that you can run the program, the stack, run stack without like self-compilation, just like run the stack with the libraries that I give you properly, okay? If you can't let it run, I will help you during this 20 minutes, okay? So just like raise your hand, I will come and help you. The library, yes, the libraries are the same, but the binaries and the source code, they're different. Yeah, so like if you manage to run it locally in last week, then it should be fairly straightforward to you to run this again this week. Yes.
So in the video, you have used European to find the like the commands that you want to use, like RDI and all those.
Yeah.
How do we do that with the log gadget? Because I was trying to find any commands that would directly give me those lines. But the last time when I ran, so the whole binary came up,
Right.
like with all the functions, and it's very hard to go through all of it.
So ROP gadget doesn't give you this functionality.
Okay.
So for ROP gadget, you have to use like, there is a command option that you ask ROP gadget to output all the gadgets that are contained, like that contains say pop or contain move.
Yes.
And that's the only thing that you can do.
I think I tried to do grasp or filter something.
Mhm.
So, but even then, if there was a lot of.
Yes, even though that there's still a lot, and you have to
Okay.
go through that by yourself.
Okay, so in that case, is it better to use Ropium?
Right, in that case, it's better to use Chromium.
Because I haven't used Ropium yet. I was just trying to catch, so.
Yeah,
In that case,
yeah.
I'll just.
Right.
Okay, thank you.
Sure. Okay. Yes. Does anyone still have problem in executing the binary? Okay, I'll come to you. Otherwise, other people are good? Okay. All right, guys, let's work on this together. Can I know how many of you managed to leak the Leapsy base by yourself? Awesome, cool, yeah, good job. All right, so for those that you already managed to leak, feel free to continue. You don't have to listen to me right now. Otherwise, I'm gonna talk to other people that you know, so that we can work together on this. All right, awesome. So now let me share my screen real quick. Okay. Okay. I think both. Oh, let me new share my screen. All right. Yep. So I think now Zoom people and also in-person people, we should all be able to see my screen right here. All right. So first thing first, let's run this program real quick. So I'm pretty sure that you already run that. If you have the environment, zoom in. Yes, I will zoom in. Thank you for reminding me. Okay. So in your right-hand side, this is how the program looks like, right? If you manage to execute it, you should be able to see that it tells you that this is the address of the base pointer, and then this is the address of the buffer, and then it starts to read the buffer from you, right? Okay, cool. And then now the first thing that we want to do is to leak the base address. On the left-hand side, it is the template that we had. It's similar to what we had last time. And you can use Pong, template to generate a template. And then you can potentially, just read those string, parse the string so that you can get the BP, the base pointer's value, the buffer's address. So to save our time, so I'm gonna just do this already. I already do this for you guys. So there's nothing that you need to worry about. And now you just know that you have the BP's address. So you have the BP's value, you have the buffer's address. And now we're about to do the leak. Okay. So if you remember, or if you watch the video, you will know that the way that we leak is to call puts, right? Puts. So it's put s, right? Puts with some value, like a function that comes from libc, right? And in this case, we're going to use puts at libc, right? So basically, we want to say, let's use puts to output something. And then the argument is the address that stores the function start output, right? And then in this case, this is the GOT table. So in the GOT table, it stores the puts. So if you remember, we talked about dynamic linking, right? In our video. And in our video, we talked about how binaries manage to use the PLT table with the PLT session with the GOT table to fetch the address of libc's function during the runtime, right? And the way it works is that it will first go to the PLT's function, right? And then in there, it will call, it will process to find the actual puts function's address at libc, and then stores that into the so-called GOT table, right? And then inside that GOT table, there are many items. So one can be puts, the other can be things, for example, printf, things like that. So the first time that your program calls function like puts in your PLT session, it will handle the case that it will save that value into the GOT table. And then it will jump to the places that the cost table saves, right? Okay, so now let's look at the binary together real quick. Let's disassemble it so that you will have a better sense about that. Okay, so opt-dump -d stack. Okay, so if you do, and here is the PLT session, right? And then if you go to put, this is part of the PLT session with puts, right? So that means that every time that you call puts, what your program does is that it will go to here and it will try to jump to this location, right? So pay attention to this. This is jump with a star and then with the offset. So by the time that this instruction to be executed, RIP points to the next instruction. So that means that RIP will always equal to this value by the time that this instruction will be executed. Okay. So it also, this instruction says that RIP plus this offset, right? And then it will take the value from that address, and then it will jump to that where that address points to. Does it make sense? Okay, good, awesome. So now we know that RIP's value is this guy, hex 4010BB, right? So what it does here is that it will have hex 4010BB plus that offset, which is hex 2F5D, right? And they will put this all together, which is equal to this value, hex 4041A. If we do a type out, do a quick math, you know that this actually is equal to hex 404018. And then so this instruction is going to fetch the value that stores at this location. And then now let's run this dynamically using GDB, okay? Okay, good. And then let's take a look at the God table, okay? So where is 404018? And that's exactly is the address of the God table. So it's like in the God table, there is one item, and that item's address is at 404010. Okay. So I'm gonna make this a little bit more clear. Try this a little bit clearer. It's dot table, and then the address is 404018. And this is the location that will store the actual libc's address. So in fact, now let's take a look at the value at this location. Okay, so that is 4018. It's actually already shown here. This is the address. Okay, so this is where libc is at right now. In fact, if you let's take a look at the instructions here. Okay, right, just make a little bit more. So this is puts. This is the puts that are in the libc function. Okay, and if you remember this address, let's do a VM map to get the current process's address real quick. You will see that this address belongs to somewhere, which segment? I'm trying to count it, is 7FF7E. This is a little bit hard to see because the font is so big. Okay, now it's better. It will belong to like E3EB450. Which one is it? 7. Okay, it's here. It belongs to this segment, right? Because this is the start and this is the end, right? The first is start, the second is end, and this address is in between the start and end. Make sense? Make sense? Cool. Okay. So in this way that we can find the value from the God table, right? And then the God table is always at this address in this case, right? Now we have a better sense. So what we want to do is that we want to call puts and then put this value inside, right? Basically, I want puts to output a string that at this particular address. And then this address will contain the value of the of the puts function address in libc. Does it make sense? Good. Okay. So now let's suppose that we already have that value. Okay. Suppose that we got everything, and this will output us some bytes. And then we'll use that to calculate the base address. And we know that put at libc, the offset will not be changed, right? So all we need to do is have that output and then minus the base, minus the offset. In that case, then we'll get the base. And in fact, if we look at the value here real quick, this is what we have for, according to the God table, right? This is what we have, which is put in libc, okay? And the next that we're gonna do is that, okay, I'm gonna open another panel and then do opt stomp dash big T, and then the libc. Okay. And then I'm gonna grab foods. Basically, I want, sorry, typo. I want to find the offset of foods in libc, which is this value, right? Okay, so we want to have that minus that, so that we should be able to get the base address of libc. So let's try this again. Let's try this together. So that will be hex this guy, right? And then minus this value. Let's still let it output in hex. Let me see. Am I putting it wrong? Yes, it's put. Okay. For some reason, I think I'm putting something wrong value here. The reason why I'm hesitating right now is because I don't know why, but this puts is not giving me the right value. Okay, I think I know the reason. So the reason is because right now, put is not initialized, or it's because, okay, let me do this real quick. I think this value may have some problem. Okay, anyway, I think we can do another better demonstration later on when we execute this and then use our script. Okay, so now let's just go back to here. Yeah. Sorry, I can't hear you. Oh, so can I explain the concept again of how to get the base address, right? So if we look at the VM map, we know that the way that, libc was loaded is that it will be loaded at a particular base address, right? And then with the offset, and the offset comes with the library itself, but then the base address is decided by the operating system every time it runs it. So that's why if you have ASLR enabled, this value will change all the time, okay? So we want to get this value so that we can do the other ROP gadgets that are on libc, right? So in order to get that, we need to find some value, like one function's address from the current libc, and then minus the offset, so that you will get the current base address of libc in the process. Okay. Yep. All right. Cool. So now let's, yeah. Right. Exactly. Exactly. Awesome. Okay, so now let's write the exploit together. So we need to have the gadget that will call that, right? Call put at this address. And then we want to find a place that we can call put from the binary, not the library, right? Because if you are finding a put from the library, then you still don't know the base address. You will know the actual address. This is like a chicken and egg problem, right? So you have to find a put function from your local binary, which will be run constantly all the time, right? And then that's why if you look at this program, you found that it has pi disabled. So that means that it has pi disabled, right? So that means that every time that you run the binary, your binary's own instruction will be in a fixed address, will be in a constant address, okay? All right, so now let's run this, let's do this together. So I'm gonna have a leak function, and from there, we're gonna build the gadget, okay? Leak, all right. So the gadget that we're gonna be build is that we want to have the argument to be ready, right? Which is we want to have a pop RDI because RDI represents the first argument, right? We want to find the pop RDI. And then followed by that will be the actual value that I want to put in the pop RDI, right? Which is this. Right? Okay. And then we want to be able to call the function of puts. And we have to find that function of puts in the binary, in our own binary, right? And there is a place that naturally contains that, which is the PLT section, right? So we need to then go to the put, which is at this location. Okay, so let's put that in. The LT puts. So PLT puts is at 4010B0. Okay. And then pop RDI. We need to find that from our own binary, and then we can use Ropium. Load. Okay, here is pop RDI return. I'm gonna use that. All right, so now we have the pop, and then we have the address that we're gonna will be given to the RDI, and then we call puts. Okay. All right. So now we have the exploit. We need to add paddings, which should be always BP +8 and then minus buff, right? So this is the place of the return RIP that we want to overwrite. Okay. So put them all together. Let's try to send the exploit and see what it will return to us. Okay. Huh. Here we go. Finger cross. Let's try it. Okay. Exploit. Non-type 2 bytes. Oh yeah, because I didn't return it. Finger cross again. Let's try them together. Okay, cool. It outputs something, right? And now we need to parse it because the time that it returns to us is in bytes, but we want it to convert that to something. It's like one integer, right? Like a big integer, 60 bits integer. That's why we're using P64 here to pack those 64-bit integer to the bytes, right? To 8 bytes. So similar here, by the time that we receive it, we need to convert that back to something that we can understand. So what we could do is the base libc is equal to, we can use mpack, which is called U64. It also comes with the Pong tools package, U64 leaked bytes. And then I'm gonna pad it to make sure that it does have 8 bytes. All right, let's try that again. Actually, let me print. So base libc. Okay. Let's see if we can do this successfully. No, because, oh yeah, because we didn't receive a line. There we go. Cool. All right. Now we get something, right? So this is the address that we get this time. Make it more prettier. So this is the leaked address. It's actually not the base. This is the leaked put, right? Put as. Okay. And then the next is we need to convert that to, or say to calculate the leaked base address based on this leaked put as, right? And then the way is that we have the leaked put and then minus that offset of puts in libc function so that we'll get the base libc, right? Okay. And then the offset put comes from, like, as we said last time, we do opt dump dash d libc.so.6 red puts. Okay. It's this guy, right? Okay. So we know that this is 7, right? And then this comes from opt dump dash d libc and then grab puts. You can also do that from PongTools. PongTools can load this as a binary and then directly read the symbol. But now I'm just using this because I feel this is easier for me. And then we can print base of libc. Okay. And then let's try that. This is base libc. Okay. All right. Let's see if everything is correct. So to testify that, I am going to use GDB because I want to get the actual libc's address by the time that I run it. Okay. I'm going to GDB. Okay. And then I'm going to do VMMap to know the base address of my current libc. And then I'm going to continue executing it. Okay. Now it gives me back something, right? Okay. And then I need to look at that again. VMMap. It's different, right? However, it looks pretty much the same. It has a slight difference. And the reason why is because there is an A there. And this is because by the time that we receive a line, we didn't drop the last byte, which is the new line byte. So that's why here, when you say receive line, you need to have keep ends is equal to false. Okay. All right, so now let's click it. Let's try this again. All right. Let's continue. It gives us this value, right? Sorry, here, this value, okay? It's 7F1E6240800. Okay. And then come back to here. It's this guy, right? So it's the same as what we leaked. Good. So now we successfully leak the base address and of libc. Okay. So the next will be, okay, how are we gonna use this libc to send the ROP gadget that will invoke /bin/h, right? And in that last week, we talked about how to construct that ROP chain. So you prepare those values and then we call them together. However, the problem here is that now you finish this exploit. There's no way for you to send another string to the server again, right? Because the server no longer takes you any string. How can you let the server to take one more string from you so that you can send the exploit? So basically you need the server to contain this vulnerability, the buffer flow again. You want to trigger the buffer flow vulnerability again so that you can give them the next exploit string that contains the XACVE bin/ROP. Does it make sense? Does it make sense for everyone? Good. Okay, so the way, like you understand that the goal of us, right? We need to figure out a way to trigger the vulnerability again, right? So that we can send another string, which will contain the bin, the /bin/sh gadgets. Okay, so in order to do that, remember that now we have the control. We can let the program to execute wherever we want. So now let's make the program to go back to its own vulnerable function, which it will take the input again. Does it make sense? Cool. Okay, so now let's try that. So let's figure it out. How can we go back to the vulnerable function again? So in order to do that, if you remember the program, which you have the source code, right? So this is the vulnerable program. It has everything there, right? So potentially you have many choices, because you can let your exploit to call the program. So it's like right after this gadget, once it finished, you have the check function next to it. It's like once it finished this call, returns, go back to the gadget chain, it will then jump to check again, right? You can do that, or you can just like go back directly, go to the gets, so that you will have the buffer, right? So I'm going to try the second approach, which is to go back to gets. And then you will notice that there will be some problem with that, but I will show you right away, okay? So now let's figure it out that we're going to call gets so that everyone, like anyone can, it will interact with the client so that anyone can send another string again. So let's figure out the address of the binary that will execute the gets. Okay. So let's go to the check function and then find the places that they call gets, right? And if you remember, gets takes one argument, which is the buffer that will store the input that the client sends to it, right? So we also need to prepare the buffer so that it will store the string that you sent to them. So let's start with this instruction. This means that it will store the buffer at the place of RBP minus hex 40, right? And then it will call gets. Okay, so now let's make this address at the end of the previous leak chain. Okay, so it's like after that leak, I'm gonna append it with one more gadget, which is the start of gets, like with the prepared arguments. Okay, and now let's see if it works. Okay, it says some dots ELF. It has a segmentation fault, and then let's debug it together and see why it is wrong. Okay. All right. Now let's continue. Switch interactive mode. I'm going to write something random there. And I go back. It says there is segmentation fault at the address of gets, right? So we know that, okay, seems that it does execute gets, but there's something wrong over there. And let's figure out why is the case. And in order to do that, I'm going to set a breakpoint at this location, okay? I'm going to finish that. Have to start over again. If I remember correctly, this is the address it's about to execute get. All right, awesome. Now let's run this again. Okay. Continue. Okay, so this is the first time that this is stops. And this is because the first time that the program is executed normally, right? So we just let it continue. Okay, now we're here again. And this is a time that we, the attacker, makes the program to execute here again because we have this gadget, right? Okay, so now let's see what's going on here. All right, so we're at this particular address. We're gonna do this instruction by instruction. Okay, next instruction, next instruction, next instruction. Okay, now we are about to call get. And then here it shows the arguments. We know that gets only take one argument, right? So we only cared about the value of this. So RDI is supposed to store the address that will store the inputs that we give them. However, this doesn't look like as a legitimate address that can store the string, right? And this is the reason why it crashes, because RDI is not a valid place that can store the input that we give them the next. And then let's look at where this RDS value coming from. So RDS value coming from RX, and then RX comes from RBP minus hex 40, right? So, and this means that in fact, because of RBP's value is not properly set, RDI's value also is not proper. In fact, if we look at the current value of RBP, which is supposed to be somewhere on stack, right? But now it has a very weird address. It's nothing related to a stack anymore, right? And this is because the first time when we overflow the buffer, if you remember, like BP, what BP points to is the saved RBP. So right next to the saved RIP, there's saved RBP. And then because we're setting a random value there that contaminates the RBP's value. So we need to change that. We need to change RBP to somewhere else so that RBP minus hex 40 is writable. Okay, so now we need to figure it out, brainstorm where in this program that we can write to, we can make this buffer writable to somewhere so that we can have another buffer overflow. And one option will be to reuse the GOT table, because GOT table is the places that you can write, right? Because that's why by the time that you call, PLT, it will give the updated value stored in the GOT table. So now let's just abuse the GOT table, okay? So look at the GOT table again. We found those addresses. So the next address that is currently idle will be 40, 40, 60, right? Because for 50, it stores this address. And after that, we actually could use 48. But now I'm just like using 60. Any places that's larger than this will be great. So I'm going to use 40, 40, 60. So what I'm trying to do is that I will let RDI point to this address so that the rest of the program will be executable. But then in order to do that, I need to make RBP equal to RDI plus hex 40, right? So that will be 40, 40, 60 plus 40. So that will be 40, 40, 80. So now we know that we need to overwrite RBP by the time in the first time of exploit so that RBP will be able to change to this value, okay? All right, so then let's come back to the first times exploit. This is the first times exploit where we managed to leak base C, right? And if you remember the stack, the way that it works is that I can just draw the stack. So there is BP, there is the buffer, right? And we always say that BP plus 8 is the place that we store saved R, right? But then where BP is going to do, it stores the saved R. So previously, when we do stack overflow, we overflow all the way down into this address, and then we consider this part, the entire thing as added. So now we're gonna change it, because we need the same RBP to be something that will be useful for us, right? So that means that we're going to make this value to become this value. Here, become this value, right? Which is 404080. So that in this case, after the first time of exploit, RBP will become this value, right? And then by the time that the program gets again, your RDI will have the value that's like legitimate, is that we can write to that particular location. Okay, so now let's change this slightly from here. So instead of having +8, we put this value, which is 404080, right? Everything else doesn't change. Okay, and now we should be able to send something else again, right? Because we know that now we can call get, and I'm gonna just put something randomly here because I want to verify that things works as expected. Okay, so I'm gonna execute X this. Okay, and I run this again. Okay. All right, and then let's continue. This is the main function. So the continue, the first time is the first time call gets, right? And then the next time call gets. Now we have RBP's value equal to 404080, which is great, right? Because in that case, then by the time that a call gets, RDI has a legitimate value that we can write to, right? Which is 404060. Okay, and now we can continue the running. Okay, now it has a segmentation fault again, and that is because we already put a random A's value, and then the stack crashes later on. But then after that gets, we should be able to manage to put AA's there. Okay, good. So now we bypass this error by changing the value of RBP. And the next thing will be, let's do the rob gadget that we had from the last time. I'm going to just copy paste this from week 5. Okay. So we have the rob. Okay. Right, so this is what we have from last time. And then this time we have the ROP with the base libc that we already prepared, right? And then besides that, we still need to overwrite the buffer. And now we know that the buffer is at the place of EBP minus hex 40. So we want to have a hex 40 times plus 8, right? And then put this chain together. All right, so now let's try this. There we go, we got the shell. And then now you can just put your participation if you want. Okay. All right. So I'm gonna send the code with you guys. So you don't need to worry about to write it down, or you don't need to worry about to take a picture, a screenshot, or whatever. But I want to take questions. So if you have any questions now, feel free to ask. Or is there any places that you want me to explain again? I'm happy to do that. Yes. So the question is why we're doing hex 48 there, right? So that's a very good question. So let's, in order to answer that, let's use GDB and to understand the layout of the stack by the time that we're about to trigger the vulnerability again. Okay, so. Okay, so this is the second time that we're about to execute the program, right? So now we're about to call get. And then now we know where RBP is, right? So RBP is at hex 40480. I'm gonna draw this. This is the stack. And then this is RBP pointing to which is hex 40480, right? Good. And then the next is that we are going to take a buffer, right? And then that buffer's address is at RBP minus hex 40, right? So in fact, if you do a couple more instructions, so it's like right before we do call, where Pong the back will give you the arguments. So this is hex 404060, and this is if you have gets, right? Like gets, this is the address, right? And then the address at this page is hex 404060, right? So it's somewhere around, which is hex 404060. So this is low address, this is high address. Okay, so that means that now your buffer starts at here, right? So your buffer starts at here, and then your program is taking this as the stack. Here's RBP, and this is the start of the buffer. So it's like going back to this problem. You have the buffer, and then you have the RBP. And then your goal is to overwrite the state RIB, which is always at RBP plus 8, right? So the question here is that how much buffer, how many bytes are we going to write so that we can overwrite these places, which the program will consider that as the state R. Does it make sense? Make sense? If you don't, tell me. I'm happy when I have to explain this. Okay, good. Okay, yeah. So the way that a computer works is very dumb in the way that it doesn't really know where the state are. In slow case, always slow case, the state I by looking at RB. So that's why that we can abuse it. We can just change the RBP's value to somewhere else. And the program will not be able to identify that. It will not be able to see that, oh, because you're pointing out of the stack, then that place will not be the R. It will always just take RBP plus 8 as that place for state I. And the reason for that is also pretty straightforward. So by the time that this function finished, let me do this real quick. Hopefully this is, well, actually, let me take a look real quick, the source code. Okay, so this is line 42. So let's execute all the way to the places that the function returns. So this is the place that the function is about to return, right? So there's like we finish function check and it's about to return. At this place, what it will do is that if you look at this assembly, it will do leave and a return, right? So the way or what return does, as we mentioned last time, is that it will just pop the value up, right? Starting, it will look at RBP plus 8, give that value to I, and then jump to that value, right? So it doesn't really check. Is here like post any legitimate address or not, or it doesn't care. It doesn't check if RBP has a legitimate stack address. All it does is just follow the instruction. So that's why we can abuse it by giving it a wrong RBP's value, and then you kind of like change the stack location. And this is also the so-called stack pivoting. So you change the stack location to pivot that to somewhere else. Okay. All right. All good. That's for today. Thank you for coming. See you guys next week.
Since of the dot table that we are getting, after we get the address of the dot table, then from where dot we using.
Sorry, say again. After we got the God table.
Yeah,
Yeah.
so from what dot table, what are we extracting?
Oh, well, we are extracting from the God table.
Mm.
So the value stored in a God table
Mm.
is the function address in DeepSeek. So what we,
Puts address.
sorry, what the
Uh,
function address? So it's like the DeepSeek, yes, the put,
The
right?
puts,
Yes,
yeah.
sorry, I just didn't hear you. Yes, the put address.
Okay, the address of the puts is there in the dot table, and we are extracting the offset of the puts address using obj dump,
Exactly.
and then we're subtracting those two.
Yes,
So we'll get the base address from that.
right, exactly.
Okay, and one more point, like you changed the value of RBP to something else, and why did you do that? Like you said, I did stack pivoting.
Mhm.
So why did we need? Why did we have the need to do stack pivoting over here?
Because if we don't do stack pivoting, when we call get again, the current value of the argument, which is RDI,
Hmm.
the current value of RDI is not pointing to a legitimate place that we can write some string.
Okay.
So we want to still exploit the buffer overflow, right?
Hmm.
And that requires two conditions. One is you can get string from the user, from the client. And then second is there's still a stack that suffers from the buffer overflow
Buffer.
vulnerability, right? So that's why you need to make sure that you still build up a stack
Hmm.
there. Whereas why you change the value of RBP to make it to somewhere that you can write, and then make the stack overflow still exist based on that new location. Does that make sense?
And
Yeah.
so how
ahead.
will we know, like not pointing to a legitimate value?
So how to know if you're pointing to legitimate? You have to try, and then just like a normal way of making it legitimate, because mostly it's not legitimate because you write to somewhere that is not writable.
Hmm.
So that's why I'm using dot. You can also use other segment that
Hmm.
is writable, or section like BSS section.
Hmm.
That's also a writable place.
Hmm.
So like it's just in today's challenge, or just like my personal choice will be the God table.
Oh, okay.
Yeah. Sure. Hey, still showing that from some subtracting puts like